This will be the only video from chapter 6. You'll notice we're starting on section 6.4. That's because some of the previous sections are just reviewing some facts about the dot product and then things we've already talked about with the dot product and work. So for example, if a force on a particle is perpendicular to the motion, then the dot product is 0 and the work done is 0. All right, so we went over that in the chapter 5 videos. In this video, we're going to talk a lot about conservative versus non-conservative forces and what that looks like mathematically. We'll be talking about the gradient, potential energy functions in multiple dimensions. So before we talk in some generality about conservative and non-conservative forces, we're going to do this specific example. So we'll do the example right away. So this is actually, I took the function from Shankar. He computes the work done for two different paths. Okay, so he gives this function in equation 6.61 on the left right there. So I copied down that same function. So the force is a function of just position. And in 1D, we could make the statement that if the force is a function of only position, then there exists a potential energy function. We couldn't do it for friction because it depended on which direction the particle was moving, but we could do it for other functions. That statement doesn't translate over to multiple dimensions. So here, this is a function that's a function of just position, but we're going to show that the work done by this force depends on the path. So we're starting at the point, at the origin, at the point 0, 0. So I labeled it the initial point right here. And we're going to go to the point 1, 1, x equals 1 and y equals 1. Now, your book does this via these two paths, 0, 0 to 1, 0, and then 1, 0 to 1, 1. So like going to the right and then up. So they compute the work done by that path, and then they do it again going up first and then over to the right. And they get two different answers. So I'll talk a little bit about their example, but I want to do a different path because that's going in horizontal and vertical segments is easier than doing any general path. So I want to demonstrate how you might compute this along a general path. So we're going to actually go along this path right here, along this diagonal line, along the line y equals x. So we're going to go straight from 0, 0 to 1, 1. So the path y equals x will go from the initial point to the final point. Okay, so and then we can compare our answer to what Shankar gets for the other two paths. All right, so let's see. If we're going along the path y equals x, then we can just set y equals x from the beginning. So along. I want to specify that this is only true for this path. Along the path y equals x, we can say f of x comma y. We can go ahead and plug in y equals x. So we get 2x squared times y squared. So that becomes x to the fourth. Right, just plugging in y equals x. And then the other one becomes x cubed plus x cubed j hat. Right. Now, this path, so we're going from this point to this point, and we're going to break up, when we integrate, we want to compute this thing right here, integral of f dot ds. Remember, this was the expression for the work done in multiple dimensions. So the force is some given thing, in this direction, which we have no control over. The path that we integrate over is some vector that's pointing in some other direction. It doesn't have to be parallel or perpendicular to f in general. The path that we've chosen is along y equals x, and so you could split it up into a bunch of little pieces, and every one of those little pieces, I'm going to blow up one of these little pieces, ds. So ds has, and so this is just zooming in on any one of these. ds has a horizontal piece, dx in the I hat direction, and dy in the j hat direction. But dy is equal to dx. We can derive that from our path. So this is y equals x is our path. If we take the differential of both sides, we get dy equals dx. And so actually I can replace this dy with the same thing dx. So if that angle, if this angle right here wasn't 45 degrees, maybe it would be 2 dx or a half dx or something like that if it was at some angle. But there is some relationship between dy and dx because of the path. So the reason that's nice for us is that we can rewrite ds just in terms of dx. And this will be nice because this turns the vector equation into a scalar equation, a component equation that we can actually integrate. So it's really tough to work with these vectors in general. But if we can replace the ds with this thing, we can write that integral just in terms of x. So we've already written f just in terms of x. We can write ds just in terms of x. Right? These are constant unit vectors, but they don't they're not dependent on x. They're constant unit vectors. Okay, so let's see what happens when we plug in this f and this ds. So f dot ds, which we're going to integrate, but let's see what this simplifies to first. This is 2x to the fourth I hat plus x cubed j hat. So that's the f piece. And then dot I hat plus j hat dx is the s hat piece. So this is some of the stuff that I skipped from before, computing the dot product. So when you have two vectors and you're dotting them into each other, you just dot the I hat pieces together. So I'm going to multiply these two together. So it's dx, maybe I should write this just to be clear about this. Dx I hat plus dx j hat. So I'm just writing it in a way that you see that the I hat pieces are 2x to the fourth and dx. So this is 2x to the fourth dx plus, and then multiplying the other two pieces together. The j hat dot j hat is 1. So this is plus x cubed dx. So now we can plug this into our integral. So we're integrating f ds from our initial point to our final point, and so right now I'm just leaving it as I and f because I don't want to, I'm not too specific about the coordinate system right here. This is just a general statement about integrating the force along the path. But when I plug in f dot ds in terms of x, 2x to the fourth plus x cubed dx, I've parameterized my path in terms of x. So I can definitely say that I'm integrating along the path, or from x equals 0 to x equals 1. We've already taken into account the y piece and how that plays into it by keeping track of the j hat and everything. Okay, so this is the work done by the force along that path. So I wanted to write w our path. I wanted to specify that this is along our path, not, another path might have a different answer. Okay, so this is equal to 2/5. And then x to the fifth evaluated from 0 to 1, that's easy. That's 1 to the fifth minus 0 to the fifth, that's just 1. So it's just the 2/5. You're probably used to this from calculus by now. Plus 1/4. So that's 8 plus 5 is 13 over 20. So it's positive. We didn't have to get a positive number. Could have gotten a negative number. It's positive. Overall, the force lines up with the path more than it's against the path. But this is not the same answer as if you integrate along these separate pieces. So Shankar does first the horizontal plus the vertical, so to the right and then up. So that one, the answer was 1/3. That's what he gets right here. Oops, whoa, sorry about that. And then the other one, when he goes up and then over to the right, he gets 2/3. So we chose another path, just straight from 0, 0 to 1, 1 along that 45-degree line, and we get an even different answer. It's close to 2/3, but it's not the same. So in general, even if the function is just a function of position in multiple dimensions, you're not guaranteed that the work is path independent. Okay, in general, it's path dependent. Okay, so actually, so and this is going to lead us into the next section. So actually, there was a test we could have done from the beginning. To see if the force was conservative. Okay, so actually let me give you a little bit of language here. So the conclusion here, the work is path dependent. It depends on the path because we get a different answer depending on the path, even with the same initial and final points. Dependent. So F is non-conservative. Okay, so think of these words as being tied together: the path dependent and non-conservative. If our computation was path independent, F would be conservative. Okay, so think of these two things as being one and the same. So there was a test that we could have done from the beginning to see if F was conservative. And the test is this: F, sorry, I'm getting sloppy here. F is conservative, is a conservative force if the partial derivative of, well, let me be specific about notation here. So F is, there's an X component, which depends on X and Y. You can see the generalization to 3 dimensions, but we can just work in 2D and you'll get the gist of this. It has an X component and it has a Y component. So this is the force, is conservative if the derivative of the X component with respect to Y is equal to the derivative of the Y component with respect to X. Now, if you haven't seen this in multivariable calculus class yet, this funny looking D, you can treat it a lot like this. So if you've never seen this before, you might say, well, what's the difference between this total derivative and this partial derivative? So the partial derivative is, you can think of it as kind of like a warning that this function that you're taking the derivative with respect to, it depends on more than one variable than what you might be than what you're taking the derivative with respect to. So it's kind of like a warning to the reader saying, you better know what you're holding constant when you're taking the derivative with respect to y. So here in Cartesian, this is relatively straightforward. Like when we have a function that depends on x, y, and maybe z, and we take the derivative with respect to y, we're going to hold x and z constant. Okay, so for Cartesian, you can get away, in this class definitely, you can get away with just treating this as if it's just a derivative with respect to y, holding the other variables constant. But if you're wondering why this exists, you got to be a little careful. You have to know what's being held constant when you're taking the derivative with respect to that other variable. Okay, so for our function, so for our example, let's take these two derivatives and see. They shouldn't be equal, right? Because we saw that the integral, the integral for the work, was path dependent. So we don't expect that these two would give you the same thing. So our function, the derivative, so fx is this piece, 2x to the fourth. So the derivative of fx, oh no, that was after we plugged in x equals y. So we want to work with the function. This is why I should put a warning here, x comma, and then we're plugging in y equals x. So remember how before I wrote f of x comma y? I had to be a little bit more careful about that, because if I don't remember that that's what I did, this is just in terms of x, not x comma y. So going back to this, this is fx right here, 2x squared y squared. Oops. And if we take the derivative with respect to y of the x component, so dfx dy, looks like we got 4x squared y. For x squared y. And then if we look at this, the derivative of the y component with respect to x, let's see what we get there. Looks like that's just y squared. Derivative of x times y squared with respect to x. It's just y squared. So these two are not equal to each other. If they were equal, then we would know that our force was conservative and that computation for the integral of f ds would have been path independent. But because these aren't equal, it was a path dependent computation. Okay, so now for this next section, make some general mathematical statements about conservative forces. So I'll just write the following are equivalent. So if any one of these things is true, then the rest are true. Okay, so it introduces a little bit of notation. Okay, so so dfx dy, if that is equal to dfy dx. Okay, so that is equivalent to f being conservative. F is conservative. So that's what we said in the last section, that these two things are one and the same. And if one is not true, the other one's not true. Okay, and we also saw that this is related to the integral of f dot ds from some initial point to some final point. This is path independent. So if either of those first two things are true, then this third thing is going to be true. Right? Any one implies all the other ones. A corollary to this last one is that if we integrate such that our initial and our final point are the same, so if you ever see an integral sign with a loop inside, it means you return back to your starting point, or it means closed. You could think of it as it's a line integral, and then you come back to, your path comes back to your starting point. So this is 0. Okay, and a favorite math problem, if you haven't taken the math class yet, they love to show that one of these implies the other one by taking your closed path and splitting it up into two path-independent pieces. And then most importantly, and the biggest tie-in with this section, you'll see that there's a potential energy function, U. Okay, so if F is conservative, if any one of these other things is true, then there exists a function U of x comma y such that F is the negative gradient of U. Okay. So first of all, you may have never seen this symbol before, this triangle. So what this means in Cartesian coordinates is that you take a derivative of your function u with respect to x, and then that's your fx piece, and then take the derivative of the function with respect to y, and that's your y component. And then you could imagine if we had a third dimension, you do minus du dz, and that would be fz, f comma z, or f subscript z. Okay, I want you to notice that this function is a scalar function. There's no vector sign on the u. But after we take a derivative, we can take the derivative with respect to any one of those variables, x, y, or z. So it's after taking so this is a special kind of derivative that takes a scalar valued function to a vector valued function. And this math symbol that does it is called the gradient. Right? So we're just introducing these terms. If you want to read a little bit more about it, you would read about the gradient. Right? Later on, in physics 4C, we'll need a couple other things called divergence and curl. But for this class, gradient is the most important and the one that we'll need. The minus sign doesn't have to be there. Like in a math class, you might see this without the minus sign. In physics, we keep the minus sign in there because we want to interpret U as the potential energy function associated with that conservative force. So U is the potential energy. So there exists a potential energy if the force is conservative. If the force is not conservative, like friction, then there doesn't exist a potential energy function. Right. The reason this condition exists, so by the way, so let me point out, let me scoot this out of the way. So let me point out that this right here is fx, right? And this is fy. So if I look at this condition on the very top, if I take the derivative of this with respect to y, it's the derivative of u, it's the second derivative of u, right? If I take a single derivative of this, that's two derivatives of u. But one of them is with respect to x and one of them is with respect to y. And if I take the derivative of this with respect to x, then that's, again, a second derivative of u. Once with respect to, first with respect to y and then with respect to x. So the reason this is related to this right here, down here, is because of the equality of mixed partials. So it's because it doesn't matter. So if u exists, if you have this function here, you take a derivative with respect to x and then you take a derivative with respect to y, you will get the same exact thing as if you switch the order in which you take those two derivatives. If you take the derivative with respect to y first and then with respect to x, you'll get the same thing. So you should try this out. Try absolutely any function that you can think of as any function of x and y, and take the two derivatives in different orders, and you'll get the same thing every time. So try and find something where that's not true. Okay, so it's the reason that you can do it in any order that leads to this condition. Okay, so you should see the relationship between that first star and the last star. Okay, this is the gist of this section. And so your homework is going to have you show whether some, so your homework will do two things. First, you'll be expected to compute work along a specific path. And also you should be able to test whether a function is conservative or not. Okay, one final example, and this will be an example. It's a little different from this one in this section, but it's the same ideas. One final example. And that is reading a potential energy graph. So this has to do with reading a graph of u of x. And we're going to go back to 1D for this section. All right, just because it's hard to draw graphs in multiple dimensions. This section is going to introduce a little bit of terminology. Okay, so let me, so the graph, or sorry, the example that we have in mind is we have two atoms. One of them will be at the origin, and then the other one is at some position along the x-axis. So the point here is that the distance between the two atoms is x. Atoms have the property that if we were to graph what the potential energy looks like, so it turns out, so I guess that's the first thing. Electrostatic forces are conservative. So there exists a potential energy function describing the potential energy between these two atoms. What this looks like as a function of x, so if the atoms are really far apart, the electrons will want to bond, so the potential energy goes down. Okay, just in the same way that so see this graph on the left right here? The potential energy as a function of x. If you pretend that was a hill, like you're on some landscape and this is a hill. If you put a marble down at any one of these points, like put a marble down at point B right here, it's going to roll down the hill. Okay, so in nature, if you set a system up, it's going to naturally go towards decreasing potential energy. And this is related to the fact that the force is related to the potential energy. So the force is in the direction. So this is actually exactly what this equation right here is implying. So it's a little hard to read in multiple dimensions. So in 1D, what this is saying is that the force is in the direction opposite the slope of u. So like if I focus at point B right here, the derivative of u as a function of x is negative, right? That's a negative slope. The derivative of u is negative, but with this extra minus sign right here, that's positive. The f is positive. So the x component of the force is positive. And so if I start a particle at rest from point B right here, it's going to feel force in the positive x direction. Or in other words, it's going to roll down the hill. Okay, so this relationship between force and potential energy says that a system is naturally going to evolve towards lower potential energy. These atoms, infinitely far apart, we'll call that zero potential energy. They want to be close together. They come together. There's a force of attraction. But then if you squeeze them too close to one another, the electron clouds overlap, there are nuclei repelling each other, they don't like it, and so they try and get away from each other. So this is what the potential energy function looks like. This thing right here. So there are some formula approximating what this looks like. If you're interested in this, you might want to look up Leonard-Jones potential. I think I butchered the pronunciation of the names. The point is that there is some equilibrium distance between the two atoms where they're happiest, where it minimizes the potential energy. So what I want to do is I want to talk about what happens if you start off, pretend you grab one of the atoms and you pull it so that it starts off right here at XA. And you start it off at rest. So what that's saying is that there's this much potential energy that you have, and you have zero kinetic energy. Okay, so if there's zero kinetic energy, then your total energy is equal to your potential energy, and you are right here in total energy. So this is your total energy. So the setup was start system from rest. So there's no kinetic energy from rest at x equals XA. Okay, so we started at, so they're farther apart than they want to be. So there's going to be a force pulling them together. So what happens is that the potential energy goes down. So there's a force in the negative x direction. So the potential energy goes down and the kinetic energy increases. So remember, as long as you only have conservative forces, then mechanical energy is conserved. So if mechanical energy is conserved, then delta potential energy plus delta kinetic energy is equal to 0. So as potential energy goes down, if delta U is negative, the kinetic energy goes up by that same amount. So no matter where the second atom is, let's imagine this one is much, much heavier, so it's fixed at the origin, and it can't really move very much. So wherever this other particle is in rolling down the hill, how this is describing whatever energy difference that is, that's describing how much kinetic energy you have. It's whatever's, if you go down in potential energy, then you still have some energy left, and that goes to kinetic. Okay, so the work done by the conservative force increases the kinetic energy. Right? The force is in the negative x direction, the particle is moving in the negative x direction, so the work done is positive, and the kinetic energy goes up. Okay, so by the way, if your total energy is negative, and you might wonder, well, how could that be? That's okay. You can always add a constant to potential energy, and it doesn't affect anything. Because the energy isn't big enough to get to x equals infinity or x equals 0, because this increases without bound right here. This is called a bound state. So this is an example of a bound, bound state. The particle doesn't have enough energy to escape. It's kind of trapped in this well. Okay, so if you don't have enough energy to get to infinitely far away, then you're bound. The Earth is bound to the sun. We don't have enough energy. We have some kinetic energy going around the sun, but we don't have enough to escape the sun. Right. Okay, so the particle is going to move to the left. It's going to increase in speed until it passes this equilibrium position. It's moving to the left, so it's going to overshoot it, but it's going to start slowing down. So the force is going to become in the positive x direction once we go on this side of the equilibrium position. And we only have enough energy to get up to this point right here, to get up to xb. So these 2 points, xa and xb, are called turning points. xa and xb are turning points of the motion. Those are the extreme values of where the particle can be. The particle can only be between xb and xa because it only has enough energy to go between xb and xa. The maximum kinetic energy of the particle occurs when it is at the equilibrium position, right? That's the biggest amount of kinetic energy because it's the lowest potential energy. So if we had some specifics for numbers, we could find out what that maximum kinetic energy is. So what winds up happening if you start off with these two atoms, they oscillate around their equilibrium position, right? So they'll go back and forth between xb and xa. So they have zero kinetic energy at the turning points, and then there's maximum kinetic energy at the equilibrium position right there. Okay. Yeah, that's a lot.